Have you ever wondered if the grappling guns used by our favorite superheroes and game characters could actually exist? Well, in this video we are going to design one and test it right here on this climbing wall. A grappling gun actually consists of two separate mechanisms. The first one is the one that launches the hook, and the second one is basically a winch, just like the ones in off-road vehicles. In this video, we will focus on the winch side. A winch consists of four main parts. The first part is a power source, that is the motor, battery and the controller. The second part is a gearbox that reduces the motor's speed and increases its torque. The third part is the rope that the winch will pull and the spool to wind the rope onto. And finally, there needs to be a chassis that holds everything together. Let's start with the power unit. Like my radial compressor, I will use two 775 DC motors. This time I will use a much more powerful 43 amp motor driver to control them. So I hope to be able to run both of the motors with a single driver. Finally, I will power the system with a 4-cell lithium polymer battery. Now that we have chosen our motors, we can think about how to mount them to the chassis. This is where the sponsor of this video, GLC CNC, comes in. Normally I use 3D printing, but since the motors can get really hot, that could cause problems. So for this, we will go with aluminum. I quickly designed a bracket that fits the motors and uploaded to GLC CNC. For this project, I'm thinking of a concept with red on one side and blue on the other, like my channel logos. So I want to paint the bracket accordingly. Luckily, GLC CNC also offers anodizing services, which lets you choose different colors and surface finishes. I'll have one bracket anodized blue and the other one red. All I need to do is select the surface finish I want, and my order is completed. It arrived in about a week and a half. Let's open it up. Yep, Customs opened the package earlier and left a little gift while doing so. But I'm lucky, the scratch is on the underside of the part, meaning it won't be visible after assembly. I'm opening the rest of the package carefully to avoid more scratches, and as always, it's spotless. The coating quality is excellent, the colors are vivid, and the finish is applied evenly. The fillets, surface transitions, all exactly how I want it. I really enjoy seeing my own design in 3D print too, but this is a whole different pleasure. It feels so much more professional. Like it's on another level. I mounted the motors using two M4 screws and both sides are ready. It looks fantastic. You too can place your first order with a nice discount using the link in the description. Now that we have mounted the motors, we need to find out whether they are powerful enough to lift me. Actually, I showed in this video that even the smallest motor can lift very heavy weights. So technically yes, these motors can definitely lift me. But the real question is, how fast? It wouldn't be great to rise at a snail's pace. To figure this out, I will use potential energy and power. Power times time equals energy. The energy we are interested in here is potential energy. Mass times gravitational acceleration times height. I weigh 75 kilos and let's say the winch weighs another 5, making the total mass 80 kilos. We can take gravitational acceleration as 10 meters per second squared. Our accuracy isn't great anyways, and our height is 1 meter. So our energy is 800 kilogram meters squared per second squared, or 800 joules. I estimate the total power of our motors to be 200 watts. Power times time equals 800 joules. Since watts times seconds equals joules, that means the time is 4 seconds. So the two motors can lift off 80 kilos up by 1 meter in 4 seconds. The motor's power isn't bad at all. So if I can hang for 40 seconds, theoretically they can pull me up 6 to 7 meters. We will see how well the theory matches the reality on the actual climbing wall. Now moving on to the stage 2, the gearbox. And this part is a bit trickier. After all, if I were to attach that pulley directly to these motors, they definitely wouldn't be able to lift me, because their torque is low, but they spin very fast. With the gearbox, we need to reduce that speed and increase the torque. So what kind of a gear ratio do we need? This part is a bit complicated, because I don't have a datasheet for the motors, so we don't know their exact torque and speed values. Based on sources I found online, for similar motors with the battery I'm using, I estimate about 12,000 RPM at 4 kg 4 cm. But when we calculate the power from these values, it comes out to almost 500 watts, which isn't really possible. Maybe the motor can reach that power momentarily just before burning out. So when calculating the gear ratio we'll use, we need to be a bit conservative. It's better for the system to be a little slower but capable of lifting me, rather than fast but unable to lift. Now let's do a ratio calculation. It will be easier to calculate from torque. The motor's torque is 4 kg 4 cm, meaning it can lift 4 kg from a lever arm with 1 cm. We'll be using two motors, so our input torque is 8 kg 4 cm. Let's assume the pulley is about 1 cm in radius and our actual torque can be way lower than what we are calculating. If we can achieve a gear ratio of roughly 1 to 120, we can multiply the torque by 120, bring it up to 960 kg per centimeters. This ratio is much higher than necessary, but as I mentioned earlier, having a higher ratio is more beneficial than harmful. As the gear ratio increases, the pulley will turn more slowly, and the gears will inevitably need to be larger, which means some material is wasted. But these aren't critical issues. If the ratio is too low, the winch won't be able to lift me, which defeats the whole purpose of this project. So I would rather have it higher than necessary, as long as it's not excessive. So how do we achieve that 1 to 120 ratio? Of course, by using compound gears. I'm planning to use 3 sets of gears. Now by selecting 3 different gear ratios, I need to achieve a total ratio of about 120. These numbers represent the ratio between each gear set. Since they affect gear sizes, they can be at minimum 3 to 4 and maximum 8. There is no exact rule here. The first numbers that came to my mind were 6, 6 and 4, which multiply to 144. Close enough. So for the first 2 sets, there needs to be about a 6 to 1 ratio between the large and the small gears. And smaller the gears I use, the better. It reduces material usage, shortens printing time, and allows me to make a smaller chassis. The gear tooth size I'm planning on using is 3 mm, so the smallest number of teeth I can use is 9. This is because the motor couplings I have need to fit inside the gear. And also, the smallest usable gear with 3 mm modulus is about 9 teeth. To find the number of teeth for the larger gear, we multiply the smaller gear's 9 teeth by the gear ratio of 6, which gives us 54. But I'm going to use 53 instead. Can you guess why? I'm looking forward for your guesses in the comments. For the last set, the smaller gear can have 14 teeth, and then the total ratio will be a product of all ratios. 53 over 9 squared times 53 over 14, which is about 131. The less small gear being bigger is also beneficial, since it carries the most torque. And now a bearing can fit inside, which will reduce the size of the frame. Alright, we know our gear sizes, so next is the chassis. Honestly, a really cool design like Tenness's Glow would be amazing. But both making it and printing it would take a lot of time. Plus, if I ever need to make any changes, I would have to print it all over again. And after the project is finished, it would just be useless. Instead, I will use aluminum extrusions. This way, it will be much cheaper, easier and more modular. Finally, there's the pulley and rope. For that, I will use this 3 mm rope with a 250 kg breaking strength. Although with nuts, it drops to about half, so roughly 125 kg, which should be enough to support me. For the pulley, I will use the 6 mm steel square rod left over from my compressor videos. I'm a bit worried since it's quite thin, but it should hold up. The plastic gear will drive the square shaft directly. There's a risk of stripping out, but I'm hoping the gears will be wide enough to prevent that. With everything ready, we can move on to the design. We are starting with the first gear. The motor will turn the larger side, which has 53 teeth, and the 9 teeth side will turn the next gear. I'm also adding bearing pockets on both sides. In the middle gear, again the larger side has 53 teeth. It will be turned by the previous gear. The smaller side now has 14 teeth. I'm adding bearing seats to this one too. If you notice, this gear is thicker than the first one. That's necessary, because it will experience nearly 6 times more torque. The last gear again has 53 teeth. This time it has a square shaft hole in the center, and holes for an adapter to distribute the load. The adapter looks like this. It increases the contact area that turns the square shaft. Our final and smallest gear is the one attached to the motor. It has 9 teeth and will turn the first gear. Lastly, the pulley. It also fits onto the square shaft. The chassis looks like this and will be made out of aluminum extrusions. I also made various shaft holders and a plate for electronics. Let's start assembling. I begin by fastening the shaft holders to the profiles using T-nuts. Then I mount the profile I'll be holding onto. I tapped M6 threads at the ends of the profiles so I can easily connect them with dome head screws. I line up the vertical extrusions with the horizontal long ones. Then I attach the extrusions that will connect everything at the corners. Drilling all these holes and tapping the ends took forever, but it's still much easier than joining them one by one with L brackets. Let's place the vertical side profiles. Some parts are identical, but for those that will carry more load, I use stronger 3D print settings. For example, the inner shaft holders here are printed to be more solid and durable than the outer ones. Let's add the remaining pieces. Now it's all starting to take shape. I'm adding caps to the exposed corners. Moving on to the gears, starting with the big ones that will turn the pulley. I attach the adapter to the gear that will help rotate the shaft. I repeat the same steps for the gear on the opposite side. I insert the square shaft through the gear and secure it in place. I also made washers to fill the gaps between the parts where needed. Then I attach the pulleys and install the opposing gear. Finally, I attached end stops. Since everything will be tight-fitting, they won't come out easily, though over time they might shift a little. Moving on to the middle gears, I installed their bearings and washers, fixed the holders and attached them to the profiles. I repeat the same steps for the other side. For the first gears, I install their bearing holders and assemble them with washers and fasteners. Then I mount them onto the chassis. I repeat the same steps for the other side. I attach the motor gears to the couplings and fasten them to the motors. Lastly, I secure the motors. The electronics and wiring is done. I have a voltage regulator to power the Arduino, and I have a motor driver that controls both motors. And I have 3 switches that basically turn this on and off, changing the direction and changing the speed. Now comes everyone's favorite part to comment out in every single video of mine: lubricating. For the motor gear, I'm not using grease. I'm using thin machine oil. Whatever I put there will be get thrown off anyway, so at least it won't fling grease everywhere. Let's test it. I'm starting with a small weight, just 8 kilos. It should easily lift that on the slow setting. And it does. The motor sound doesn't even change. Let's lower it and add more weight. Now it's at 16 kilos, which is all the weights I have at home. It can lift that on the slow setting too, though I think the sound changes slightly. I lowered again and I noticed something. Making the grip directly from the extrusions wasn't such a great idea. Even at this weight, it started to hurt my hand. To test with more weight, we're at the Calisthenics Park. While we're here, if you enjoy working out, learning new skills, or just trying new things in general, you might really like our new channel. On that channel, where we constantly learn new skills, the first video where we learn stand-up paddleboarding in just 2 days will be released the same day as this video. Since it's a new channel, if you check it out and if you end up liking it, subscribing to it would really help it push in the YouTube algorithm. Reaching 1,000 subscribers with the first video would be amazing. The links to that video and the channel is in the description. Let's get back to the winch and see if it can lift me up. I have set everything up. I attached the rope to the pull-up bars with a carabiner, and for safety I have my helmet on and safety glasses. So let's go! I don't want to hang right away, so let's play a game of tug of war first. While I try to stop the winch, I want to thank the 7 members who support me in making these videos. You can also click the join button and become a member to help me with these projects. It's impossible to stop. Even if I put all my weight into it, it doesn't flinch. We tried it with 2 people, but it just keeps going. Now I will try hanging. Let's clean up the slack. Since the bar is quite low, I have to crouch quite a bit. Switching to the fast setting, and it lifts me up easily. Sadly, I will have to stop it at the carabiner. So yes, it can lift me up, but this place isn't really enough to do a proper test. I need somewhere higher. A 15-meter climbing wall about the height of a 4-story building should be enough. Before testing again, I had to swap out the pulley. The old one was completely destroyed. Now it has 100% infill, but whether it will be strong enough, I'm not sure. The rope I'm using isn't technically rated for carrying a human, so I'll be wearing the necessary safety equipment, and a friend of mine will blame me. First I need to climb up the wall and attach the rope to the top anchor. To do that, I tie one end of the rope to my harness, and my friend connects himself to the rope as well, using a blade device that can break and stop the rope if needed. As I climb, I clip these carabiners into the bolts along the wall, attaching the rope through them as I go. This way, if I fall, I'm secured to the wall. It's actually a fairly easy route overall, but since I haven't climbed in a while, it's quite challenging to me. Once the rope is clipped onto the top anchor, we collect the gear and head back down. The rope stays attached to the wall's fixed anchor. But I'll need to climb one more time, this time to attach the winch's rope. The bolt on the balcony should be enough for testing. The rope I'm using for the winch is shorter than the wall anyway, so it won't reach the top. And now the moment of truth. Let's see if the winch can actually lift me. And yes, it can. It's just a little slow. Sure, but I expected that. I knew I wouldn't be able to hang for long, so I clipped the winch to my harness with a sling. I only need to use my hands to guide the rope to neatly wind onto the pulley. Even though it's slow, it lifts me all the way up to the balcony, smooth and steady. It's slightly faster on the way down, but the difference is minimal. That tells me the gear ratio is really high. The small amount of friction into the motor's gear is enough to support my entire weight. If you haven't checked out the new channel, go ahead and check it out now. Seriously, go watch that video. Afterward, I ran a few more stress tests. The pulley broke again, and there were some minor deformation on the motor's gears. But aside from that, it actually worked really well. Thank you so much for watching. So far, this has been the hardest video to make, shoot, organize and edit. I hope you liked it. I'm looking forward for your suggestions and ideas in the comments. I also want to thank the 7 channel members who helped me make this video. And this video's sponsor, GLC CNC. Don't forget to check out their coupons and services via the link below. See you in the next project. Goodbye.